Nice. Let's go. So hello everybody, my name is Adrien Suau, so I'm a third year PhD student at LIRMM. My advisor is Ada Todori-Sanyal from LIRMM. I also have several co-advisors. First one, Eric Bourreau from LIRMM. He's mostly working in optimization. Gabriel Staffelbach from Surfax. So Surfax, from those of you who don't know, it's a laboratory in Toulouse working in computational fluid dynamics and numerical resolution of PDEs related to fluid dynamics. And also Marco Ronchik from Total, because my PhD thesis is financed by Total, or Total Energy now. And so today I'm here to talk a little bit about quantum computing, so one of the emerging technology. Not knowing what was your level in terms of quantum technology, and knowing that a lot of hype has been around since the last few years, I just wanted to make a little bit of state of the art of what exists and where we are right now in the field of quantum computing. So in terms of algorithms, here you have a kind of time map or time lapse of the important algorithms with their invention date or publication date. All of them are quite important. The first one is the first algorithm to have any kind of speed up on a classical, on a problem. So basically the Dutch JOS algorithm here is the very first algorithm to show that a quantum computer can theoretically outperform a classical one. The second one, Grover, and the third one, Shor, are probably the most famous quantum algorithm. You probably know about them if you looked a little bit into the field. So Grover algorithm is basically searching in a list. For example, most of the time it's presented as searching in an unsorted list. And the second one, Shor's algorithm, is an algorithm that has been invented by Peter Shor that basically is able to factor integers in their prime factors in a polynomial time, which basically breaks a lot of the cryptography we have right now. So it's probably the most famous algorithm in quantum computing. Fourth one, HHL, from its inventors, Arrow, Acidim, and Lloyd, is an algorithm that came out in 2009 about solving linear systems on a quantum computer in a time that is logarithmic in the size of the system. So you have a lot of fine prints, a lot of little conditions to check in order to use this algorithm correctly. But if you check all of them, you are able to solve a linear system in a time that is logarithmic in the size of your linear system. And then the two last ones are VQE for Variational Quantum Eigensolver and QAOA for Quantum Approximate Optimization Algorithm. These two are a kind of new paradigm of quantum algorithms that I will explain just later, but basically they are more suited to the hardware we have right now. Now, in terms of software, so I just spoke about algorithm, but you can't program a quantum computer without software, So in terms of software, in the last few years, and by few I mean 4-5 years maximum, a lot of frameworks appeared in order to program quantum computers or to build the quantum programs we want to execute afterwards on quantum computers. Here I listed several of them. So basically Qiskit is from IBM, PennyLane from Xanadu, which is not well known for the moment. Cirq and TensorFlow are from Google. MyQLM is from Atos, French company, and Bracket from Amazon. So a lot of big names here that tries to impose their framework as the standard way of doing quantum computation or of programming quantum computers, actually. And with most of them, you can actually access real hardware. You have also several frameworks and libraries that are starting to appear in the field. And now, so algorithm, software, but the most important part is hardware, because without any hardware, we can't actually execute anything. So in terms of hardware, you have several companies, some of them being well known in other fields, such as IBM and Google, or others that are just startups or a little bit more than startups specialized in quantum computing, like Rigetti and IonQ, have hardware, actual quantum hardware. So I listed here the number of qubits of the biggest chip and the number of chips they are providing. For example, IBM is providing approximately 20 chips, and 6 or 7 of them are freely accessible. If you want to access them, it's possible. You don't have to pay anything, you just have to log in into their website, and you can actually submit a circuit on their quantum chips and start to have a kind of trial and error, trying to execute circuits. On the right here, what you see is a quantum computer from IBM, for example, here. So the actual chip is just here. It's a very small part here, and the whole thing above is the circuitry and the electronics in order to control the chip. So all the information will go down these cables up to the chip, which is here. And everything will be enclosed in a big fridge because everything is cooled down, very, very cold. Here at the very bottom, where the chip is, you have a temperature that is approximately 3 millikelvin. So very cold. It's a dilution fridge you have here. And yeah, just a quick warning. So here I listed number of qubits and number of chips. But you can't say from this number, OK, Google chip is better because it has more qubits. This is not true, because you have a lot more data that is important in order to assess the quality of the chip or what you can do with it. For example, error rates, or qubit quality, or the fact that your qubits are coherent. They stay coherent for a long time. Or again, chip topology. I will talk a little bit more about this later, but chip topology is very important. For example, IBM topology is not all-to-all, so you have a kind of nearest neighbor topology, whereas IonQ is all-to-all. So basically, if you take the 65-qubit chip from IBM and the 32-qubit chip from IonQ, they are not really comparable, and in the end, the IonQ one might perform better on some use cases. So this is about the hardware. But as I told you, okay, the hardware we have right now is noisy. We have a lot of error rates. To give you an idea of the error rates we have, measurement error rate for IBM and Rigetti also, I think, is of the order of the %. Sometimes it's even higher. Like some of the oldest chip from IBM, you have some qubits where you have a 10% chance of having the wrong measurement, which is huge. Same about gates. So you have 1 qubit and 2 qubit gates in quantum computing. The typical error rate of 2 qubit gates is 0.1%, something like this. So if you end up executing 1,000 2 qubit gates, the final result will basically be noise because your gates are just too noisy. There is a specific term to qualify these chips. It's NISQ, N-I-S-Q, which stands for a noisy intermediate scale quantum, meaning that you have a quantum chip that has a little bit less than 100 qubits, and all the qubits are very noisy. So NISQ chips are the chips we have right now, less than 100 qubits and noisy operations. Now, how can we actually improve the quantum computer? Because for the moment, we have very limited chips with a big error rate, and it's hard to use because of the error rates, because of the limited number of qubits. So how can we improve the quantum computers we have right now? First idea, first solution, we improve the quantum computer. So basically, there is a lot of engineering involved. We improve the error rate, we improve the topology, we improve the design process, we improve the engineering process in order to have a chip with more qubits or lower error rates, better fidelity, qubits that stay coherent for a longer time, things like this. So this is mostly in the physical side, engineering side. Not really my side. On my side, I'm more a software guy, but other people in LIRMM, like Ada or C1 and other PhD students, are looking at this. You have also the way of improving the control software. So just like in classical computing, you can improve your processor, but if your compiler is bad, you will end up having bad performance. So you can also improve the control software by improving compiler, improving error mitigation techniques also, or improving ways of analyzing and optimizing the quantum circuits you are sending to the chip. if you can, for example, remove 50% of the gates from your circuit and have an equivalent circuit by just halving the number of gates with optimization techniques, you will end up having better results, because less gates means less errors. Third idea, we can also improve the algorithms and the actual implementation of their implementation. So if we have a better algorithm, we might end up having less gates, so less errors. Or if we have a better implementation of a given algorithm, same principle, less gates, less errors, and we end up having better results. And this is what we looked at a little bit. So now this was the theory, a broad overview of what is possible and what we are targeting. Now I will show you some examples of what we've done. First on implementation, and then on tools, on control software and tools in order to help improving the implementation or help improving the execution on the actual quantum chip. So first, when I did this, I was at Surfax, as I told you, computational fluid dynamics, and the idea was to answer the question, can we actually solve a PDE, a partial differential equation, on a quantum computer? Is it interesting? Can we do it first? And if we can, then is it interesting? Is it interesting in terms of runtime, in terms of resources needed, etc.? So in quantum computing, we have two ways of solving PDEs. First way is very close to the classical computing way of doing it. We discretize our PDE using whatever scheme we need, and we solve the resulting linear system using a quantum algorithm, HHL algorithm here. I told you earlier, the algorithm to solve linear systems. The second way, which is more oriented toward quantum and more adapted to quantum computer, is to rephrase the PDE as a Schrödinger equation. Because Schrödinger equation is actually exactly what the quantum computer is able to solve very efficiently. So if we are able to rephrase the PDE as an instance of the Schrödinger equation, then we can solve the Schrödinger equation and recover our solution efficiently using a quantum computer, at least in theory. So before my PhD, we found a paper that did this on the wave equation, 1D wave equation. So we implemented it. We implemented the algorithm that rephrased the 1D wave equation into a Schrödinger equation and then solved it using a quantum algorithm. And our goal was first, is it working? Are we able to actually get back the result of the wave equation by simulation? And the answer was yes. So next step is, okay, how much does it cost? And when will we be able to solve partial differential equations on a quantum computer? And we ended up with these kind of schemes here. So basically here, what you are looking at is, I want to solve my 1D wave equation with a given number of discretization points. How much qubits will I need in order to solve it, in order to execute the implementation of the quantum algorithm on a chip? And here, what is very interesting is the scaling. If you look at the scaling, which is here, it's logarithmic. So your resources will scale logarithmically with respect to the number of discretization points. Meaning, roughly, if you add 3 qubits to your implementation, to your quantum computer, you are able to solve a problem that is twice as big, because there is a 3 here in front of the log, which is kind of interesting. Then we looked at the number of gates. So we looked at the number of qubits, but then how many gates should we execute on a quantum computer in order to solve these kind of equations? And here, so same x-axis is the number of discretization points, number of gates is y-axis, and you can see that the scale is very high. The constants are very high, in fact, which means that whenever, here, if you look at the plot, you have something like 10 to the power 8 gates. If you have a 0.1% error rate per gate, executing that much gate, it's out of the question on real quantum computers we have right now. Maybe later, but right now, this kind of implementation and this kind of algorithms are not suitable for the hardware. So this was basically our conclusion. It's interesting in terms of resources, but it's not suitable for hardware we have right now. And I'm not an hardware guy, but I would say that the consensus in the community is that we won't have chips that can execute this kind of algorithms is in the next 10 years, for example. And this is where variational algorithms come into place. So the previous algorithm was basically, I'm building one big quantum circuit, one quantum program, and I want to execute it once on the chip, or several times on the chip to get back the result. Variational algorithms are a little bit different. We encode our problem as a cost function that is computed on a quantum computer, and we try to optimize using a classical optimizer our cost function. So here you have the classical optimizer, and you compute your cost function on an actual quantum computer. You have the cost that is returned by the quantum computer, and you try to optimize this cost in the optimization loop. What is interesting with this kind of algorithm is that the circuits you end up submitting on the quantum computer are very shallow. You don't have a lot of gates. You execute more circuits, but all of them are very small, which is okay when you have high error rates. You can still hope to recover some kind of results, meaningful results, because you don't have a lot of gates. So this is still a work in progress, but yeah, basically same questions. Will it work? Can we solve PDEs with this? How much does it cost? Will it scale good or not? And can we actually execute this on real hardware? Because the previous algorithm, we kind of knew from the start that it was not suitable for real hardware. These kind of algorithms should be suitable for NISQ hardware, so near-term hardware we have right now. And this is a question we are trying to answer for the moment. So now, stopping about algorithms, more on the tool side, on the compilation and analysis and optimization of our program. We've done also several things. First of all, when we started the implementation of the wave equation solver 2 to 3 years back, we've realized that a lot of tools we were used a lot of tools that exist in the classical world were not present, were not existing in the quantum world. For example, a profiler. You probably already used a profiler, I don't really know, like Prof, Qprof, Intel VTune, or things like this. These are tools that will analyze your program, your classical program, and tell you, okay, this function is a hotspot. You are spending 80% of your compute time in this function. So if you want to optimize something, try to optimize this function, because this is the function that takes the most time. And this kind of information is very interesting in order to optimize the implementation. And there were no tool in the quantum computing community to do this, to spot the hotspots in quantum programs. So basically, we implemented one called Qprof. So we based the implementation on Qprof, which is one of the profiler in the classical programs. And that's why we called it Qprof, so Q for quantum and profiler prof. And it works quite well. So to visualize how it works and what kind of results it gives, here on the left, you have a quantum circuit. So each, just to explain you a little bit the visualization, each line here, horizontal line, represents a qubit, one different qubit. And each square here, or this kind of thing here, represents a quantum gate. So here, I'm applying the H quantum gate on the third qubit. Here, I'm applying the C0 quantum gate between the second and the third qubit, etc., etc. And so this is one of the possible representation of a quantum program. It's basically kind of a visual representation of the assembly. It's approximately at the same level of the assembly. But this kind of representation, when you have a circuit with thousands of gates, it's just not visually speaking, you can't analyze it because there is too much information. And so the goal of Qprof is to get this kind of graph here, which is a call graph. Basically, the routine called 1C6 circuits calls the routine called C6 that in turn calls H, CX, T dagger, and T with the execution time and the relative execution time in the rows here, and a color to spot the sensitive point, the odd points. So here, in this kind of implementation, the CX is the gate, CX, which is this one here, this gate and all of these gates here, is the gate that takes the most time to execute. So on this small example, it doesn't seem that useful, but for a biggest example, for example, Grover algorithm with 10 to maybe more thousands gates, you end up having something that is readable, whereas 1,000 gates or 10,000 gates is just unreadable, and you can't reason about this. You can't optimize anything from this. So here, yeah, this is a kind of tool we are building. So everything has been open sourced. It has been like we submitted a paper about this, and yeah, it supports right now from the framework I showed you last time. It supports 2 of them, Qiskit and MicroLM, but we plan to support more because, as you saw, a lot of framework. We have a lot of framework in the quantum computing community, and the goal is that we support all of them, even though it's a hard goal. It would be perfect to support all of them. Now, changing a little bit the subject and coming back to compilation of quantum circuits. Here, what you can see is the actual topology of a quantum chip. So it's one from IBM called IBM Sydney, IBM Q Sydney. And this is a topology. So basically, when you come back here, this is the 2-qubit gate, a C0 gate. It's the only 2-qubit native gate that can be executed on the hardware. And it can only be executed between qubits that are linked. So circles here are qubits. Links are the possible communication between qubits for 2-qubit gates. When you develop your quantum programs, you don't want to be hardware dependent. So you don't actually take care of, okay, do I have a link between qubit 1 and qubit 4? You just want to develop your quantum software, to develop your program, but you don't take care of the topology of the hardware because you might want to execute on different hardware with different topologies. And so adapting your quantum program to the hardware is the goal of the compiler. And the compiler should be able to adapt your program that is generic to the specific hardware topology that the specific hardware you want to execute your program on. And we've done a work on this with my not roommate, it's the other PhD student that is working with me about compiling quantum circuits by taking into account error rates for the different operations. And it gives good results when we compare it with the state of the art. At least it gave, because a lot of work has been done on this since then, because it was 2 years ago, and so everything is improving quite rapidly. Another kind of work we are doing right now, my C1 is doing right now, C1 new is doing right now, is most of the circuits we are trying to execute on the hardware for the moment are very small. 5 or 10 qubits maximum for the moment, because we are at the very early development steps, exploration steps, so we are executing small circuits. So 10 qubits, let's say 10 qubits, but the hardware has here 27 qubits, meaning that we don't use the hardware fully. And the goal of the other project would be that if you have, for example, 2 circuits with using 10 qubits, you might be able to execute them in parallel on the hardware using different qubits. For example, these 10 qubits here for the first circuit, and these 10 qubits here for the second circuit. These give rise to a lot of challenges because you have some kind of crosstalk between the qubits. If they are linked here, they might experience errors between each other. If you execute an operation, for example, here between these 2 qubits, you might see errors on this qubit because it is linked with these 2. And so, yeah, it's multiprogramming. It's called multiprogramming, and you have the paper here about multiprogramming on how to increase hardware throughput without actually losing some kind of fidelity. So thank you for your attention. I've included a lot of information in the slides. You have the slides available here, along with some links, like links to all the papers, and links to frameworks, links to quantum hardware, links to everything. If you are interested, you can have a look. Thank you.